In this video, we'll discuss how to find a basis of a row space. We'll dive right in with the method theorem. To find a basis of a row space, perform Gaussian elimination and keep the non-zero rows. This theorem is based on a theorem we've already seen. Row spaces are clearly finite dimensional because the rows are a finite spanning set. And we have this theorem that says if we have a finite spanning set, we can turn it into a basis by finding vectors that are linear combinations of other vectors and removing them. Let's see how this works with a matrix. Our first row will be 1, 2, 3. Our second row, 4, 5, 6. Our third row, 2, 1, 0. And let's do a Gauss-Jordan elimination on this, or maybe just Gaussian elimination. Remember that this Gaussian elimination doesn't change the row space. So we'll start by multiplying the first row by -4 and adding it to the second row. Then we'll multiply the first row by -2 and add it to the third row. -4 plus 1, that is -3, -6. And the row space of this matrix, the row space of this matrix, the row space of this matrix are the same. Now, we'll multiply let's name these rows. We'll multiply the second row by -1, and we'll add it to the third row. And the third row becomes all zeros when we do that. In other words, by this point, in the process, we had made the second and third row equal. So notice we can't necessarily expect that all the time, but the third row is a linear combination. Sorry, that's not addition. The third row is a linear combination of the second row. Sorry, I don't know if you can see this stuff popping up on my screen. If I seem a little distracted, that's why. And our theorem says that if one row is a linear combination of others, we can get rid of it without changing the spanning set. So the third row was a linear combination of the others. We got rid of it. And the linear combinations are in general precisely the vectors that get turned to zero by Gauss-Jordan elimination. The vectors that survive have therefore been reduced to a basis. This process of performing Gaussian elimination and getting rid of the zero rows is precisely the process of finding vectors that are linear combinations of other vectors and removing them. Our basis then is the first and the second row. Notice a difference between finding row spaces and finding column spaces. With column spaces, you performed the Gaussian elimination to find the pivot positions, but then you had to go back up and use the original matrix. Because Gaussian elimination doesn't change the row space, we don't do that here. The row space of this matrix is the same as the row space of this matrix, and we can therefore use the rows of this matrix as our basis. In this video, we've seen how to find a basis of a row space. Moving on, we'll see how the dimension of a row space, the number of vectors in that basis, is related to the dimension of the column space.